In this video, we will learn how to use the chart of nuclides to help us make some predictions about an isotope's stability. The chart of nuclides is a plot of the number of neutrons versus the number of protons. And when all of the known isotopes are plotted, a pattern emerges. The first thing we see is that all of the stable isotopes, which are shown as black data points, form a very narrow band that increases as the number of protons or as the atomic number increases. So that band deviates upwards. The other thing we notice is that all of the unstable isotopes, which are shown in purple, form a wider band that surrounds the stable isotopes. So in other words, there are isotopes that are above the stable band, there are some that are below the stable band, and there are some that are beyond the stable band, because you might notice that the stable isotopes stop just a little bit above 80. In fact, all isotopes with Z 83 or greater from bismuth on are all unstable. Now, where an isotope happens to fall on this chart of N versus Z can help us predict the type of nuclear decay that that isotope will undergo. So if the isotope has an N to Z that's too high relative to what should be stable, then that particular nuclide will tend to undergo beta decay, as opposed to an N to Z ratio that is too low compared to what is stable. Those isotopes will undergo either positron decay or electron capture, and sometimes both. Now, there's no way for you to know which one it is, positron decay or electron capture, and so when you're making the predictions, you would just include both of them. And finally, those isotopes that are beyond the stable band, in other words, those with Z equal to 83 or greater, tend to undergo alpha decay as their primary mode of nuclear decay. So what we can do is we can calculate the N to Z ratio for a particular isotope and then make some predictions about the expected mode of nuclear decay. Now, one of the things that we have to do in order to make the prediction is we have to have an idea of what is considered a stable N to Z ratio. And as you saw from the chart, it depends on Z. So as you increase Z, the stable value of N to Z also increases. Now, there is a simple approximation that you can use, and I'm going to go ahead and write it down here, and it depends again on Z. So if we have Z and N to Z, and I'm just going to write down the values of Z in increments of 10. So we have 10, 20, 30, 40, 50, 60, 70, and 80. Because again, our stable isotopes stop at 82. And then the N to Z ratio, so you would remember that it starts at 1.1 for those isotopes that are less than or equal to 10. And then it goes up for most of these increments of 10 by a value of 0.05. So when we're at 20, the stable value would be 1.15. Now, the only difference to this sort of simplified version is when you go from 20 to 30, it jumps up to 1.25, but then all of the remaining Z values go up by 0.05. So then for 40, we're at 1.30, then 1.35, 1.40, 1.45, and 1.50. As I mentioned, I'm going to say it again, this is a rough approximation. So there are, full disclaimer, plenty of isotopes that are completely stable, but that deviate from this general scheme. This just allows us to make an approximation so we can get a sense of what's going on. So this will be our comparison. This will be our reference. All right, so to solve the first problem, for phosphorus 35, I'm going to start by writing the full AZX notation. So we have phosphorus, the mass is 35. We look up phosphorus on the periodic table, and we see that phosphorus has atomic number 15. And then we can calculate our neutrons by subtracting. And now we have our neutrons, our protons, and we can calculate the N to Z ratio. So the N to Z ratio is 20 neutrons divided by 15 protons. Rounding to 2 decimal places, we get 1.33 for our N to Z ratio. So that's the first part, calculating N to Z. The second part is comparing that to what we expect for a stable isotope. So for phosphorus, our atomic number, our Z, is 15, which is between 10 and 20. So we expect a stable value of N to Z to be between 1.10 and 1.15, approximately. And when we do that comparison, we see that our calculated N to Z is too high. So 1.33 is quite a bit higher than 1.15. So we know that this is an unstable isotope, and because that N to Z ratio is too high, the primary mode of nuclear decay would be beta decay. In our second example, we have radium-218. So writing our notation, 218 for the mass. Radium has atomic number 88. So 88 for Z. Subtracting these, we get 130 for the neutrons. Calculating N to Z, we have 130 divided by 88, which gives us 1.48 for our N to Z ratio. Now, if we take a look at our table here that shows us the approximate stable N to Z's, we're reminded that the chart, or that this guideline, stops at Z equals 80. That's because all isotopes greater than Z equals 82 are unstable. So this isotope is unstable, and those higher Z isotopes, greater than 82, tend to decay by alpha decay. In this particular example, the N to Z ratio isn't helping us. It isn't part of how we are predicting the mode of decay, because this isotope is a higher Z, because it's greater than 82. But the problem asked us to calculate the N to Z, so we did, and we predicted the mode of decay. In our next example, we have gallium-66. And gallium has an atomic number of 31. So we will get our neutrons. So our neutrons are equal to 35. And when we calculate our N to Z ratio, we have 35 divided by 31. And that gives us 1.13 for our N to Z ratio. So we'll look at our approximation. Gallium's atomic number Z is 31, so it's around here. So we would expect a stable N to Z ratio to be around 1.25. And we can see 1.13 is quite a bit less. So the N to Z ratio is too low, and when it's too low, the primary modes of decay are positron decay and or electron capture. Our last example is for sulfur 34. So we'll go through this one more time. So we have a mass number of 34. Sulfur has atomic number 16. So we subtract to get our neutrons, and our neutrons are at 18. So calculating our N to Z, we have 18 divided by 16, which gives us an N to Z of 1.12. So looking at our chart, for Z equals 16, it's between 10 and 20. So we expect a stable value of N to Z to be between 1.1 and 1.15. And in fact, this number, this value of N to Z that we've calculated seems to fall in that range, and we would call this stable. Remember that stable nuclides do not undergo nuclear decay, so there is not a primary mode of decay for this stable isotope.